This video is going to serve as an introduction for a virtual field trip in which we try to show you what the rocks that would comprise the various structural units you see in this model would actually look like if you were to see them in the field. This model has already been discussed on this page. I'll put a link to its video in the top right corner. But the reason we're looking at it here as far as the field trip goes is that you can easily see very distinct structural units within this model. I'm outlining one of them here, and these structural units, if you compare the first one to the smaller one here, have very distinct appearances in terms of internal deformation, and they are geometrically very different. This is a very large unit here, comprised of a great deal of material. This is a much smaller structural unit. You've got these thin thrust sheets stretching out towards the very edge of the deform zone. They're sort of their own distinct unit. I've got these flat-lying sedimentary layers that were not deformed at all during the preparation and production of this model. That's a distinct unit, and so on and so forth. And the reason that the size or geometry, and particularly the thickness of these units is significant is that thickness corresponds with the potential for burial depth. And maximum burial depth and the temperature encountered at maximum burial depth is very important in determining whether we classify the rock that we're going to see here as metamorphic or as sedimentary. If rock gets buried deeply enough and is subjected to sufficient temperature, along with other characteristics like elevated pressure and fluid content, then that rock will undergo textural and mineralogic changes that we define as metamorphism. So making sense of where you find metamorphic rock in the Appalachians versus where you find sedimentary rock requires that you be able to visualize the mountain range in terms of its internal structural architecture, sort of in the way that you see here, and that you also be able to take these structural units and relate those back to the undeformed model, sort of relate this stuff back to its starting position on the edge of a continent, on the edge of ancient North America. So if we look at the model prior to its deformation, got a rigid continental block here. That's what this dark foam represents. This is sort of an undeformable mass. Nothing's going to happen to it really during the deformation of the model. On top of that thick continental block, got a very thin sequence of layers. As we move out towards the thinner edge of the thick continental block, there's a lot more layering. So this deformable sequence of layers here is about 3 times as thick as it is here on top of the full thickness continental block. And if we move further out towards this indentar mass, the sedimentary section here, these are representing sort of layers of sediment that have been deposited off the edge of the eroding continent. It becomes thinner and thinner, and then we have this thicker mass that would represent maybe an approaching island arc or the edge of another continent. And the reason that, again, thickness and depth is important is that's what's going to control exactly how deep these layers end up below the top of the deformed wedge. And you can actually take each of these starting parts of the model and relate those to a structural unit in the final deformed version. So this very thick sequence of layering here corresponds to this structural unit. This zone where thickness tapers pretty quickly towards the thin section corresponds with this smaller structural unit, and then the very thin layer sequence on top of the continental block corresponds to these thin thrust sheets at the very edge of the deformed zone. And the reason that this very large structural mass is particularly significant is that the deeper layers here are already pretty deeply buried, and when we actually start deforming the model, shortening and compressing this sequence, folding and thrust faulting will occur, and this sequence will become even thicker. That increased thickness puts these layers even further below the surface, their burial depth increases, and that burial depth in the real world would be sufficient to produce metamorphic change. Now that would start to occur at 200 or 250 degrees Celsius. In this case, the deepest part of this sequence would be buried much more than that. We'd be looking at something like 15 kilometers or more in this part of the model, And if you assume that temperature is increasing at 25 or maybe 30 degrees Celsius per kilometer in an orogenic setting like this, these layers might see 450 or maybe even about 500 degrees Celsius. That's going to be sufficient to produce significant metamorphism, and if erosion exposes the deeper parts of this big structural unit, you're going to see metamorphic rock at the land surface. So this is the metamorphic structural mass, the metamorphic thrust sheet. Some of the shallower parts of it, they might not have been buried deeply enough to undergo metamorphism, but certainly in a place like the Appalachians, all of this top material is eroded away, and you're looking at sort of the roots of this mass, and indeed everything you see in this part of the model is going to have reached sufficient depth for metamorphism and will appear to you as metamorphic rock with metamorphic textures and mineral assemblages. Now this transitional zone, where the layer pack is tapering from thick to thin, at the deeper parts of that there can be significant burial. There's also good tectonic burial as the leading edge of this thrust sheet buries this zone more deeply, but this is never going to reach full metamorphic depth. When you see these rocks at the surface, they will show evidence of temperature increase, they will show evidence of intense deformation, but they're going to look very distinct from the metamorphic rocks that you're going to see in the adjacent thrust sheet that brings fully metamorphosed material sort of over top of this transitional zone. So you might see rock here that would look like what you might call a slate or maybe a phyllite, depending on exactly how deeply it was buried, but certainly this material is distinct from what you'd see over here. These thinner thrust sheets that correspond to this thin layer pack, there's not going to be sufficient burial depth for metamorphism there. You're looking at burial that's going to be certainly under 10 kilometers, and that under 10 kilometer burial is not really going to do much in terms of mineral growth and textural changes that we would consider to be metamorphism in the sense that we've defined it for these other masses. So this is all going to be sedimentary rock. Even though it's folded and thrusted, it's going to look like sedimentary rock to you in the field. This is going to look like sort of a transition between sedimentary and metamorphic rock. And then this is fully metamorphic rock with mineralogy and texture that's not going to really look at all like the starting material would have looked like. And to make sense of this in terms of actually where you are and where we're going on this trip in the Appalachians, you can actually compare this model and its internal structural units to what you can see at the land surface today. If you look at this hillshade map, here I've overlaid hillshade DEMs on top of Google Earth, you can see that there are distinct parts within the landscape. I'm outlining one now. This is what we call the Blue Ridge. Got a very broad valley here. That's also a distinct topographic zone. Have a very distinct ridge and valley topography here, and then a very deeply dissected plateau region at the leading edge. And indeed, these topographic zones correspond to structural zones. So this plateau area that you see here is undeformed sedimentary rock. This valley and ridge zone is folded and thrusted sedimentary rock that was never buried deeply enough to undergo metamorphic change. This broad valley corresponds to the transitional zone, where burial probably exceeded 10 kilometers, maybe looking at 12 kilometers or so, right at the very borderline for metamorphism to begin, but certainly not enough to produce the full-blown metamorphic change that you see in rocks exposed in this part of the range, which we call the Blue Ridge, and this is the metamorphic Appalachians, everything from sort of this ridge to the east or towards the core of the ancient orogenic wedge. Now, what you see here today is very different from what was present at the end of mountain building. Every bit of rock that you see within the view we're looking at here at the surface today has been exposed by the removal of overlying material. So every rock you can put your hand on here today was buried underneath of at least a kilometer or so of overlying rock at the end of mountain building, and certainly here in this part of the Appalachians under several kilometers of overlying rock. So erosional loss has been greater in what was the thicker part of the orogenic wedge, that is to say, where you see metamorphic rock exposed today, that erosional loss becomes a little bit less as you move out towards the edge of the deformed zone. When you get into this area, you'd be looking at the removal of only a kilometer or two of overlying material. But suffice it to say, significant erosion of what was once a much thicker orogenic wedge has been required to make this landscape look like it does, and also to sort of expose these more interior parts of the wedge at the land surface today. Now additionally, the Appalachians have been rifted apart. We'd have to sort of split the wedge in two here. That was the result of opening of the Atlantic Ocean. All of this material comprises the continental crust of northwest Africa today. If you were to match this part of the Appalachians in southwest Virginia up to what we call its conjugate margin across the Atlantic, you'd be looking at the country of Mauritania. So we don't show that in the model. We don't show isostatic adjustment to the thickness of this wedge in the model. Don't worry too much about that. Just take away the fact that erosional loss has been very significant in places where metamorphic rock is exposed, and that erosional loss is much less significant in places where you see sedimentary rock today. So we're going to take you from the metamorphic Appalachians about 70 kilometers to the very edge of Appalachian deformation and show you metamorphic rock, transitional rock between metamorphic and sedimentary, and then deformed sedimentary rock that's going to look very different in terms of texture and mineralogy from the metamorphic rocks we look at in the first stop.